we've been talking about coordination compounds, and isomers are common in coordination compounds. Isomers are compounds that have the same formula but different structures. So we saw a little bit with isomers before, but now we're going to see a lot more. So there are two broad categories. We have structural isomers and stereoisomers. In structural isomers, the atoms are connected in different ways. Instead of carbon, oxygen, nitrogen, you might have carbon, nitrogen, oxygen, right? So they're physically connected in different ways. And there are two subgroups of structural isomers. You can have coordination isomers or linkage isomers. In coordination isomers, the ligand and the counterions can exchange places. A ligand can become a counterion can become a ligand. And then we also have linkage isomers. Some of the ligands can attach to the metal with different atoms. So like nitrite, NO2 minus. It can attach to the metal with the nitrogen atom or with an oxygen atom. That gives us different connectivity. Those are different compounds, different isomers. The other category is stereoisomers, where the connections are the same, but the arrangements are different in space. We can have geometric isomers where there are different spatial arrangements around the metal ion, and these are cis-trans or fast-mer isomers, and we'll talk about those. Or we can have optical isomers, and this is a special case where two compounds are mirror images of each other, but they cannot be superimposed. So let's start with structural isomers. Coordination isomers, when a coordinated ligand exchanges places with the uncoordinated counterion. So here we have two examples. So here we have a cobalt ion and 5 ammonias, a bromide ion and a chloride ion. Here the bromide ion is one of the ligands on the central metal ion, and the chloride is the counterion. So when this compound dissolves in water, the chloride is going to go off floating by itself. Here, the chloride and the bromide have switched places. Now the chloride is bounded to the cobalt and the bromide is not. So when you put this compound in water, the bromides float away. So they have the same chemical formula, they have the same molar mass, but they are different compounds. Any questions? Of course, coordination isomers can only happen with charged ligands. You can't have ammonia becoming a counterion because it's not an ion. Linkage isomers have ligands that coordinate to the metal in different orientations. The nitrite ion, it can attach through the nitrogen or through an oxygen atom, and then these have different names. If it attaches by the nitrogen, it's nitro. If an oxygen attaches, it's written ONO, and it's called nitrito. So here we have the ligands that are capable of this type of isomerization. So here, the nitrite ion, if it attaches by one of the lone pairs on an oxygen, it's called nitrito. If it attaches by a lone pair on the nitrogen, it's called nitro. The cyanide ion, both the carbon and the nitrogen have lone pairs. Either one of them can donate that lone pair in a coordination bond with the metal ion. Isocyanate and thiocyanate can also be have linkage isomers. So here we have a ball and stick model, and this is the NH3,5 around the cobalt, and here we have the NO2. In this one, the nitrogen is attached to the cobalt. In this one, an oxygen is attached to the cobalt. So you can see the different structure here. The formulas would be written slightly different. NO2, the N is first because that's what's connected. Here, ONO, O is first because the oxygen is connected. And then the names will be a little bit different as well. And if we look at these substances, they have two different colors. So just by changing which atom is connected to the cobalt, that changes the physical color of the substance. And that's an example of a linkage isomer. Any questions? Stereoisomers. So geometric isomers happen when the ligands bonding to the metal have different spatial arrangements. Let's see. So we can have cis-trans isomerization in square planar complexes. So if your square planar complex has the formula MA2B2, where you have two ligands of one kind and two ligands of another kind. So there are two different options. We can put the similar ligands next to each other, or we can put the same ligands across from each other. So in order to turn this one into that one, you would actually have to break those coordinate covalent bonds and reattach them. You can't just rotate it in space and have it be the other thing. So here, the like ligands are next to each other. They are on the same side. If you imagine a plane cutting through here, right? This is on one side, this is on the other side. Here, these are on opposite sides of that plane of symmetry. Okay, so cis is a prefix that means the same, and trans is a prefix that means opposite. And those have the same meanings that we use in everyday life as well. Any questions? We can also have cis-trans isomerization in octahedral complexes, where we have 4 ligands that are the same and 2 that are different. And so that's what I'm working on putting together here. Let's do these guys. Got my model kits. And of course, the models I have made are for the end of the lecture. So I have to remake enough of those, right? Have to take those apart. And I'll have to put them back together again. There we go. So we've got the illustration there, but this is, a very three-dimensional thing, and sometimes it's hard to visualize. If you're going to take OChem next, you might consider just getting the OChem model kit now, because it could be helpful. But you can also make your own models at home using gumdrops and toothpicks, or colored marshmallows and toothpicks, or, get out some clay or something. Toothpicks seem to be like the universal stick thing. You can make your own at home. Okay, so here's the illustration of the cis isomer. Oh, and I just realized I made these wrong. Okay, I can do this. I really can. One step ahead of myself here. Go on to the next kind of isomer. Okay. So I've got blue and yellow, blue and orange, and this has blue and green, but you get the idea. So here we have this octahedral complex, and it's helpful to be able to see this shape. So what I visualize the octahedral as is, this is a little girl, and she is a ballerina, and so this is her skirt. Oh, missed a piece there, right? And so we have her head and her feet, her body, and then there's a skirt around. And so this is a model like that. And so both of the orange ones are in her skirt. And if we rotate this way, we see they're next to each other in the skirt, right? So here they're green. Those two like ones are next to each other, and so that is a cis isomer. In this version, we have the like ligands across from each other. So we can draw it this way, where the ligands are in the skirt again, but they're not next to each other, they're across from each other. Or we can even tip this one 90 degrees, and now those orange ligands are her head and her feet, and the skirt is all blue. But the orange, or in the picture, the green, are across from each other, and so that's the trans isomer. Any questions? Fast-Mer isomerization happens when we have an octahedral complex where we have 3 of one kind of ligand and 3 of another. So FAS is for facial, and MER is for meridian. Okay, so let me make this again. See if I can do it right. So again, we can visualize this as the little girl's head and her legs, and this is her skirt, right? So here, her head and half of her skirt are green. The other half of her skirt and her feet are blue. So that's going to be like this one, right? This is called a facial isomer, and the reason for that name is that these 3 like ligands define one of the faces of the octahedron, right? So an octahedron has faces, right? Triangular faces. So this is one face, and then the other that are similar, the other 3, define another face. So that's the facial isomer, or the FAS isomer. Then we have the MER isomer, or the meridian isomer. And here, the like ligands form an arc around the central metal ion. So these are forming an arc, and these guys are forming an arc, right? So there's 2 arcs. If you continued this, around, right, that would be like a meridian, something that goes around the middle. So here's the MER isomer lined up the way it is in the picture, and we see this is an arc. This is not making a triangle, right? It's making an arc around the central atom. We could also put it up like this, where we've got her head and half the skirt. We can do it like this. Now we see the orange ones are around the equator, the meridian, right? But it's not all those. There's an extra one over here that's different. Okay, so that's the meridian isomer. So on exam 5, there will be a question that asks you to draw and identify the different kinds of isomers. But the great news is this won't be an in-person closed book exam, so you don't have to memorize these things. Isn't that nice? You can just look them up. So I'm telling you about them, and then you can figure it out when you do the exam. There's some homework questions too. Okay, Draw the structures and label the type of all the isomers of each complex ion. Okay, so this is the sort of question that could show up on that exam. So each of these has 6 ligands. It's going to make an octahedron. And so the way to start is by just drawing the skeleton of an octahedron. So here we have our metal ion in the middle, and there's going to be something going up and something going down. And there's going to be one that's kind of poking out at you on that side and on the other side. And then there's going to be one that's hiding behind. So instead of writing all the letters, we're just going to use colored circles. I'm going to use blue for the water and green for the chlorine, the chlorides. So the first one, you can just kind of go willy-nilly, just like, oh, well, whatever. Let's do blue, 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 and green, green, green. And then we ask ourselves, well, what kind of an isomer is this? So with this combination of 3 and 3, we can have a Fas or a Mer isomer. So this is like this model, right? Where you can take the 3 like ligands and they form a triangle, one of the faces, right? And here's the other one of the faces. So this is the Fas isomer because this is one of the faces and this is the other one of the faces. So we need to be a little more careful when we draw the other isomer because we want to make sure that we don't just draw the same isomer turned around, right? So if you have a picture of someone's back and a picture of their front, the pictures look different, right? But they're pictures of the same thing, right? So we don't want to end up with that. We want to end up with pictures of different things. So again, I'm going to start by just making the octahedron in the, the skeleton here. And now I want to be careful about where I put things. A lot of times, you just need to exchange one pair. So I could exchange this blue one and that green one. So I'm going to keep this one green and that one green. And I'm going to make this one green. And these stay blue. And that one becomes blue. And now I have drawn this model, where these 3 blue ones do not make a triangular face of the octahedron, right? They're making an arc around the center, and this is making an arc around the metal ion. So what kind of isomer is this? It's the meridian. So the names for these ions, you would put this prefix in front of the name for that formula. So this is -3 chloride, so this must be chromium 4. So this would be tri-aqua, trichloro, chromium 4. So we'd say Fas, tri-aqua, trichloro, chromium 4, or Mer. Any questions? So, Mer, tri-aqua, trichloro. chromium, ran out of room, 4. So you might have a homework problem that gives you this name and says, draw the structure or pick the structure out of a bunch of pictures. And then we've got this one. So this one we have 2 ammonia and 2 chlorides and 1 oxalate. So this is 5 ligands instead of 6. We didn't talk about this in the lecture, right, part, but we can figure this out. So if you remember back to Vesper theory, the shapes of molecular compounds, when we had 5 electron groups, they would arrange themselves in a trigonal bipyramid. And so that's going to be our central metal with an up and a down, and 1 is off to the side, and then there's 1 in the back, and 1 coming out towards the front. I thought I had one of these made yesterday, but I guess I did not. I don't even have the right pieces to make one, so... Oh wait, I can do it with this one. So we'll have 2 ammonias and 2 chlorines. And 1 oxalate. Oh, hang on a minute. So I overlooked this in lecture yesterday, and I just about overlooked it again. Ox stands for oxalate. Oxalate is a bidentate ligand. It attaches in 2 places. So this is still an octahedron. So we can fix that. Let's get rid of that guy. This is an octahedron still. And so, let's see, I'm going to make the ammonia blue, and the chlorine's going to be orange, and the oxalate's going to be red. So I've made a model here, and so what you do for a bidentate ligand is it attaches at 2 points and then it's connected, right? So the oxalate has to attach next to itself. It can't be across. So let's put the oxalate in first. So let's make this the oxalate. And the oxalate is connected. It occupies 2 of the positions on the octahedron. And then we can make the other ones. So here's this one and this one. And these 2 guys. So that's the model that I've made right here. Let's see. I can make the other one. These are boring videos, extra boring, I should say, videos to watch at home because you can't see any of this, which is why you're supposed to come to class. Just saying. Okay. So here's the other one. Let me draw that. So I'm going to keep the oxalate in the same place. It's easier to see what's going on if you change as little as possible. And so I'm going to swap this one and this one. And so now I've got something that looks like this. So that's this guy. Do you see what's different? In the second one, the chlorines are opposite each other. Here, there's no like ion or like ligand across, right? So this would be considered a cis ion, or cis isomer, sorry. And this is a trans isomer. But there's actually one more, because here we have the orange being trans. What if we made the blue trans instead? Are these two the same? Can we just move them around? Let's see. Switch this one. So this one actually has 3 different isomers. So in this one we have the chlorines, the orange ones opposite of each other, and here the blue ones are opposite. And I can twist these around all day, and I cannot make them the same. They are different. The only way to make them the same is to pull them apart and make different connections. So this is also a trans isomer. Any questions? Note to self, do not post yesterday's lecture on YouTube. Okay, so the other type is stereoisomerism. So optical isomers are non-superimposable mirror images of each other. And these are said to be chiral, C-H-I-R-A-L, chiral. That's a word that gets used a lot in organic chemistry. So this is a little preview of chirality so that when you take OChem, you won't be shocked. So we actually have an example of chiral things on our bodies, actually more than one. But our hands are the easiest to look at. You have a right hand and a left hand, and it doesn't matter if you can't tell which is right and left. They are the same. You can put your palms together, and they're the same size. They look the same, right? But can you superimpose them? You can try like this, but your thumbs and your pinkies line up. And if you try to put your hand into the wrong glove, you realize this isn't very comfortable because the thumb is angled in the wrong direction. So your hands are the same, but they're not the same. They're chiral because they're mirror images of each other. If this hand looks in the mirror, it's going to see this hand, right? But you can't take this hand and turn it around and put it on top of the other. So these are chiral. Enantiomers is the name for isomers like this, and they exhibit optical activity, which means if you have a solution of a chiral substance, and you have one isomer or the other, and you pass plain polarized light through the liquid, it will twist the light either clockwise or counterclockwise. It's really kind of trippy to see. Sugars do that. So we'll see this in tetrahedral complexes if you have 4 different ligands, or we can see it in an octahedral complex where we have bidentate ligands. So here we have 3 bidentate ligands. So when this isomer looks in the mirror, that's what it sees. So now I have to go back and make what I just tore apart. See if I can do it without dropping any of them on the floor. So because these are bidentate ligands, they have to be next to each other, the 2 attachment points. We can't have one here and one down there because the ligand isn't big enough to do that. So here I've made one. Try to make the other one. When you make these or when you draw them, it's easy to accidentally make the same thing. So I just made one and I made the other, and I'm going to look at them and see if they're the same or not. So we have to kind of line some things up. And I made the same one. So do you see how these are superimposable? I can line these up so I've got, for you, this one in the back, that one on the front left, and this one on the lower right, sorry. Those are the same, right? If this one looks in the mirror, it's not going to see that one. We have to move some things in order for it to be, is that gonna work? Yeah. The mirror image. This is why making the models yourself at home with whatever you've got is really helpful, because then you can actually twist them around and look at them. So now I've got mirror images, right? So if I take this one and try to superimpose it on that one, I can't do it. I can get this one lined up, but then the other 2 don't line up. They're not the same. They're like your left hand and your right hand. Do we have a picture? No. So I'm going to show you the, oh good, I didn't completely destroy those. I'm going to show you the tetrahedral one as well. The tetrahedral one is what we see in OChem. Okay, so here I've got a tetrahedron, a black center, and then 4 different colors, right? And so I can set these up so that this looking in the mirror is going to see this other one. See how they're mirror images of each other? But if I try to line these up, good luck. So I can get 2 of the colors to line up, the orange and the green, but then the blue and the red and the purple are mismatched, right? The only way I can get them to line up is to swap 2, and then they're not mirror images anymore. So again, it's like your hands. So determine whether the Fas or Mer isomers of CrH2O3Cl3 plus are optically active. So what this is saying is, if you look at the Fas isomer, does it have a mirror image that is not superimposable? If we look at the mirror isomer, does it have a mirror image that's not superimposable? Or are the FAS and the mirror images that are not superimposable of each other? Well, first we have to draw something. Okay, so we've got our basic octahedron here. Oops, okay. And so we've got 3 of one kind and 3 of another. So 3 of that one and 3 of the other. Is this a FAS isomer or a MER isomer? FAS. It's a facial isomer because this forms a face, right? So this is a FAS isomer. So then what we want to do is we want to draw the mirror image of this. So in the mirror, if this is the mirror, this is the mirror up the middle, and this one is looking, it's going to see orange here, right, instead of blue, and there's going to be blue on the other side. Now, the question is, so here we've got mirror images. Are these the same? Can I take this one and rotate it just in space and have it be the same as this one? Yes, I can. If I take this one and I spin it 180 degrees, so this one comes over here and this one comes over there, I just spin the tutu a little bit, I can make exactly the same thing without disconnecting anything. Is this optically active? To be optically active, the mirror image cannot be superimposed on the original thing, like your hands. Let's see. Let's make this. So what I want to do, let's do this. Okay, so here is, oh, I made the meridian one. Don't want to do that yet. Okay. Okay, there's a FAS isomer. That's the wrong, here we go. Bless you. The nice thing about using candy to do this is when you're done, you can eat the candy. Okay, so this is a FAS isomer, like the one on the left, and this is the mirror image. See that? Mirror images. If I take this one and rotate it, now they're the same. These are not optically active. The mirror image is actually the same as the first one, right? So like a ball, the mirror image of a ball is the same as the ball, right? It's not your right and left hand are different. So these are not optically active. Whoops. Not optically active. Okay, so let's draw the meridian isomer. So to make the meridian isomer, we have to move some things, right? I'm going to swap these two. So the orange ones are making an arc, the blue ones are making an arc. This is the meridian isomer. So let's look at its mirror image. So I'm just going to, so this needs to be, that's not the right color. This needs to be orange. And that one's orange and that one's orange. And this one needs to be blue. So we got a mirror. Right? It's inevitable. They're going to end up on the floor. So, especially after playing with the models, you can get to a point where in your mind, you can take these pictures and rotate them. But it takes some practice, and you really just have to play with the models first. So here I've got models, and I'm going to try to line these up. Okay, mirror images, right? If I take this one and just rotate it 90 degrees, they're superimposable. These are the same. This one's just done a little turn to become the mirror image. Are these optically active? No, because they're the same. The mirror image is the same. So these are also not optically active. To be optically active, the mirror image has to be different, not that you can just twist it around and superimpose it. Any questions?